Did you know that over 100 million pieces of debris are currently orbiting Earth at speeds upwards of 17,000 miles per hour? These fragments, ranging from tiny paint flakes to entire defunct satellites, might sound harmless at first. After all, they're just floating in the vacuum of space. But in reality, every single one of them poses a significant, even catastrophic, threat to operational satellites, future space missions, and the safety of astronauts. This growing cloud of space junk could even trigger a chain reaction of collisions so severe that it might render whole regions of orbit unusable for decades. Faced with this crisis, a solution has emerged at the crossroads of cutting-edge innovation and environmental responsibility: advanced artificial intelligence-powered systems designed to manage, track, and even remove this debris. In today's video, we'll delve into how these systems work, the groundbreaking benefits they bring, and the remarkable vision they offer for a cleaner, safer, and more sustainable future in space exploration. If you've ever wondered how technology could solve one of the most pressing problems of our era, you're in for an eye-opening journey. To understand why advanced artificial intelligence-powered systems are becoming essential for space junk management, we first need to grasp the scale and origins of the problem. When the space age began in the late 1950s with the launch of the Soviet Union's Sputnik, humanity could hardly imagine that a simple metal sphere would lead to a growing crisis in Earth's orbit. In the decades that followed, thousands of satellites and rockets were sent into space, many of which completed their missions only to be left behind as debris. Along with discarded rocket stages, tools from spacewalks, and even chips of paint, these remnants accumulated into what's now a veritable junkyard encircling our planet. Things took a turn for the worse, however, with the advent of satellite collisions and explosions. A stark example of this occurred in 2009, when an operational Iridium communication satellite collided with a defunct Russian satellite named Cosmos. This single impact shattered both satellites into thousands of fragments, greatly increasing the amount of hazardous debris in space. Each piece, regardless of size, became a potential disaster waiting to happen. At speeds of up to 17,000 miles per hour, even a fragment the size of a marble can cause devastating damage to a functioning satellite or spacecraft. The ripple effects of this growing clutter are staggering. Active satellites, which are vital for modern life on Earth, face mounting risks. Think about the technologies we use every day: GPS navigation, weather forecasting, television broadcasts, and global internet communications all depend on a delicate network of satellites orbiting Earth. Every time space debris threatens one of these satellites, it jeopardizes the systems that power our modern world. Imagine losing GPS for a day, no navigation, disrupted logistics, and a domino effect on countless global industries. Now imagine losing access for weeks or even months. The stakes are astronomical, both literally and figuratively, and the threat isn't limited to satellite networks alone. Space exploration is also in jeopardy. The growing density of orbital debris raises the chances of collisions during launches or while astronauts are working aboard the International Space Station. It's a haunting reminder that without intervention, humanity might one day face what's known as the Kessler syndrome, a scenario where the debris field becomes so dense that a chain reaction of collisions makes certain orbits completely inaccessible. This wouldn't just delay the progress of space exploration, it could cripple humanity's ability to venture beyond Earth altogether. Clearly, this problem is not going away on its own. In fact, the more we delay action, the greater the challenge grows. As more satellites are launched, especially with the rise of mega constellations like Starlink, which plan to deploy thousands of satellites into low Earth orbit, the situation becomes even more precarious. The need for innovative, scalable, and efficient solutions has never been more urgent. This is where artificial intelligence enters the picture, promising not just to track this ever-growing swarm of debris, but to actively help mitigate it. But how exactly can technology tackle such an overwhelming challenge? Let's explore that next. Artificial intelligence-powered systems for space junk management might sound like something out of a science fiction novel, but they're very real, and they're rapidly becoming a cornerstone of our efforts to protect Earth's orbital environment. These systems leverage the incredible data processing capabilities of artificial intelligence to tackle a problem that is, quite literally, too vast and complex for humans to manage alone. Let's break it down. At the heart of these systems is the ability of artificial intelligence to analyze massive amounts of data in real time. Every piece of space debris, from a bolt no bigger than your thumb to an entire defunct satellite, has its own unique trajectory. Tracking hundreds of thousands of objects, each moving at incredible speeds, requires continuous monitoring and precision that no human team could achieve unaided. This is where AI steps in. Machine learning algorithms are trained to sift through data collected by ground-based radar systems, telescopes, and sensors installed on active satellites. These algorithms can identify objects, predict their movements, and assess the likelihood of collisions, all within seconds. This isn't just about crunching numbers, it's about making complex, high-stakes decisions faster and more accurately than ever before. But AI's role doesn't stop at monitoring. Once potential collisions are identified, AI systems can help determine the best course of action, whether it's altering a satellite's orbit to avoid debris or guiding an autonomous spacecraft to intercept and remove the hazardous object. Autonomous satellites and robotics play a crucial part in this process. Imagine satellites equipped with robotic arms or nets, capable of capturing tumbling debris and either redirecting it or deorbiting it safely. These spacecraft, guided by AI, can operate without constant human intervention, making them efficient and cost-effective tools for cleaning up our orbital highways. One of the most innovative examples of this concept is the use of smart satellites outfitted with AI navigation systems. These satellites can operate as debris hunters, locating large pieces of junk using onboard sensors and cameras. Once the debris is identified and tracked, they can execute precision maneuvers to capture it, a technological feat that would have been unimaginable just a few decades ago. Companies and organizations around the world are actively developing such systems, from Europe's Remove Debris mission to Japan's efforts in using tether technologies for deorbiting. Beyond cleaning up debris, AI also plays an essential role in prevention. By analyzing data from past collisions, machine learning systems can predict the areas most at risk and help guide future satellite launches to avoid congested zones. This kind of foresight is critical as the number of satellites in low Earth orbit is expected to skyrocket in the coming years. AI enables us to take proactive steps, not just reactive ones, in safeguarding our orbital environment. But with these revolutionary capabilities comes an important question. What is our ethical responsibility when it comes to deploying AI in space? Should there be limits on how autonomous these systems can become? And how do we ensure that their actions benefit humanity as a whole, rather than prioritizing the interests of a select few organizations or nations? As we continue to explore the potential of AI in orbit, these are the kinds of questions we must grapple with. After all, space may seem vast and limitless, but our use of it must remain thoughtful and sustainable. So, what do you think? How far should we allow artificial intelligence to go in managing our shared space environment? One of the most transformative technologies addressing the space junk crisis is the use of AI-driven tracking and detection systems. These advanced systems are redefining how we monitor and manage traffic in Earth's orbit, taking on a task that was once slow, resource-intensive, and prone to human error. Let's dive into how this technology works and why it's such a game-changer. At the core of these systems are cutting-edge AI algorithms designed to process enormous volumes of data at astonishing speeds. Ground-based radar systems and optical telescopes have long been the tools of choice for tracking debris. They scan the skies, collecting information about the size, speed, and trajectory of objects orbiting Earth. However, the sheer volume of data they generate is overwhelming. Traditional methods rely on manual calculations or limited automation to predict the paths of debris and identify potential collisions. In a world where a single satellite might need to avoid hundreds of objects in a matter of days, this approach falls short. That's where artificial intelligence steps in. AI algorithms are trained to parse this data almost instantly, identifying patterns and predicting the movement of debris with remarkable precision. For example, AI-driven systems can differentiate between active satellites, dead satellites, and smaller fragments in orbit, all while determining their exact trajectories and assessing collision risks. Tasks that would take hours or even days for human operators can now be completed in seconds, allowing for real-time decision-making. This speed is critical, especially when satellite operators only have a narrow window of time to maneuver a spacecraft out of harm's way. One of the most prominent examples of this cutting-edge technology is the European Space Agency's AI-based collision avoidance system. This system analyzes data from multiple sources, including radar stations, optical observatories, and satellite telemetry, to predict the likelihood of collisions with unprecedented accuracy. Not only does it alert operators to potential risks, but it also recommends specific actions, such as adjusting a satellite's orbit or delaying a planned maneuver. This proactive approach reduces the chance of unnecessary or inefficient movements, which can save fuel, preserve satellite lifespan, and minimize disruptions to services like GPS or communications. The European Space Agency's system effectively showcases how AI can bridge the gap between data overload and actionable insights. To put this into perspective, think about how traditional methods operate. Operators would receive raw data about potential hazards, then perform manual calculations or rely on outdated predictive models to assess the risk. This process is time-consuming, and with the ever-growing volume of debris in orbit, it's increasingly unsustainable. In addition, human error or slow responses could lead to catastrophic consequences, such as satellite collisions or damage to essential instruments in space. AI-driven systems eliminate much of this uncertainty by automating the detection and analysis processes and making recommendations based on reliable, real-time computations. Another remarkable advantage of these systems is their ability to adapt and learn. Unlike traditional methods which rely on static rules and models, machine learning algorithms can evolve over time. As they are exposed to more data, such as the outcomes of previous collision avoidance maneuvers or the behavior of certain types of debris, they improve their accuracy and efficiency. This continuous learning cycle ensures that AI systems stay ahead of the curve, even as the space environment becomes more congested and complex. The level of precision that AI brings to tracking debris has been compared to finding a needle in a haystack, but at speeds and scales that were simply unimaginable just a few decades ago. For instance, AI-powered systems can not only predict the future path of a bolt-sized piece of debris, but also account for factors like solar radiation pressure or slight variations in Earth's gravitational field that could alter its trajectory. This level of detail allows satellite operators to make informed decisions with confidence, protecting both their assets and the orbital environment. In essence, AI-driven tracking and detection systems are transforming space debris management from a reactive process into a proactive one. By significantly improving the speed, accuracy, and scalability of tracking efforts, these systems represent a major leap forward in humanity's ability to safeguard the future of space exploration and communication. But this is only the beginning. AI is just one part of a much larger toolkit being developed to address this growing challenge. So, what other groundbreaking technologies are emerging in the fight against space junk? Let's take a look. While artificial intelligence-driven tracking and detection systems are essential for predicting and preventing collisions, the next big leap in tackling space junk comes from autonomous spacecraft and robotic systems designed specifically for debris removal. These advanced technologies are not only innovative but also vital in addressing the growing problem of orbital clutter. Let's explore how these systems work and why they represent a groundbreaking step forward. One of the most notable examples of this emerging technology is the European Space Agency's Clear Space One mission. Scheduled for launch in the near future, Clear Space One showcases the potential of autonomous systems to clean up space debris proactively. The spacecraft is equipped with advanced AI and robotics to identify, capture, and safely deorbit pieces of junk. Its first mission will target a discarded payload adapter, essentially a piece of equipment left in orbit after launching a satellite. Using AI-powered vision systems, Clear Space One can precisely navigate toward the target, lock onto it with a set of robotic arms, and guide it into a controlled descent to burn up in Earth's atmosphere. This mission is significant because it demonstrates a scalable way to remove larger, potentially more dangerous debris pieces from orbit. The use of vision-based artificial intelligence is especially critical here. In space, lighting conditions, object movements, and the vast distances involved make precision navigation incredibly challenging. Vision systems, powered by AI, allow spacecraft like Clear Space One to see the debris in real time, analyze its trajectory, and make micro-adjustments to approach safely. These systems can even adapt to unexpected changes, such as the debris rotating or drifting, a level of responsiveness that's impossible to achieve through manual control. This autonomy significantly reduces the risks associated with such missions, particularly when dealing with objects traveling at thousands of miles per hour. Another exciting initiative comes from the United States Defense Advanced Research Projects Agency, better known as DARPA. Their orbital cleanup missions focus on developing robotic servicing spacecraft that can not only remove debris but also repair or refuel satellites, extending their operational lifetime. For debris removal, these robots use sophisticated grasping mechanisms, such as robotic arms or claws, to latch onto objects. Integrating AI, these robots learn from their environment, allowing them to perform tasks with minimal human intervention. This self-sufficiency dramatically reduces costs compared to traditional human-led missions, which would require highly trained astronauts, complex equipment, and extensive planning. In addition to grasping and capturing debris, these systems can also employ creative techniques for deorbiting. For instance, some concepts involve attaching small propulsion units or tethers to debris, gently pushing or pulling it into a decaying orbit where it eventually burns up upon re-entry. These methods are not only efficient but also safer for other spacecraft operating in nearby orbits. Other proposals, like using nets, harpoons, or even adhesive surfaces, demonstrate the wide range of approaches being tested to tackle debris of all shapes and sizes. One of the most compelling aspects of these autonomous systems is their ability to operate independently. Once deployed, they require minimal oversight from mission control, thanks to their AI-driven navigation and decision-making capabilities. This autonomy reduces the need for constant human monitoring, freeing up resources and ensuring missions are carried out efficiently. In fact, many of these spacecraft can be programmed to target multiple pieces of debris in a single mission, maximizing their impact and reducing operational cost. This level of efficiency is crucial as we look toward scaling up debris removal efforts to address the millions of objects currently in orbit. Looking ahead, the potential of these systems is immense. As the technology matures, we could see fleets of autonomous cleanup spacecraft patrolling Earth's orbit, working together to ensure a safer environment for satellites and future space missions. These systems might even evolve to tackle more complex challenges like cleaning up geostationary orbit, where higher-value satellites reside, or addressing smaller debris that is harder to track. With advancements in AI, robotics, and materials science, the possibilities are virtually limitless. So, while autonomous spacecraft and robotic systems are already making incredible strides, they represent just the beginning of what's possible. Their ability to operate independently, precisely navigate in challenging conditions, and perform complex tasks is transforming how we think about space sustainability. But as we dream big, there are still challenges to overcome, from regulatory frameworks to sustainable funding. Could these technologies truly scale up to meet the growing demands of orbital debris management? Let's explore what the future holds. When it comes to managing space junk, the benefits of AI-powered systems are nothing short of revolutionary. These cutting-edge systems are not just tools for solving a problem, they're reshaping how we approach sustainability in space exploration. From increased precision and efficiency to cost-effectiveness and environmental stewardship, AI-powered solutions are unlocking opportunities that were previously unimaginable. Let's take a closer look at how they're transforming the way we address orbital debris. First and foremost, one of the standout advantages of AI-powered systems is their unparalleled precision and speed. Tracking space debris is a superhuman challenge, literally. With over 100 million objects swirling around Earth, even the most advanced human-operated systems struggle to keep up. However, AI changes the game entirely. Algorithms can sift through massive amounts of data from radar systems, telescopes, and satellite sensors in real time, identifying and predicting the paths of debris with extraordinary accuracy. For example, systems like those used by the European Space Agency can detect potential collisions between debris and operational satellites days in advance and even recommend specific maneuvers to avoid them. This capability not only saves vital seconds in decision-making, but also drastically reduces the risk of human error. But precision alone isn't enough. Space debris management must also be scalable and cost-effective, especially with the rapid increase in satellite launches. This is where AI shines again. By automating debris tracking and collision avoidance tasks, AI-powered systems minimize the need for constant human oversight. Operators no longer have to spend countless hours monitoring data feeds and performing calculations manually. Instead, AI handles these tasks autonomously, allowing human teams to focus their attention on higher-level decision-making. This level of automation drives down operational costs, making debris management accessible for a wider range of organizations, including smaller companies and emerging space programs. It's a crucial step toward ensuring that space remains viable for everyone, not just a select few with deep pockets. In addition to cost savings, AI-powered systems also improve safety for astronauts and space missions. The International Space Station, for example, frequently performs debris avoidance maneuvers to dodge potentially hazardous objects in orbit. These maneuvers are complex, time-sensitive, and resource-intensive. With AI handling the detection and prediction of debris movements, these evasive actions can be planned more efficiently and with greater confidence. In the future, we might see autonomous spacecraft equipped with AI navigation systems capable of avoiding debris entirely on their own. reducing the burden on human crews and eliminating unnecessary risks. Another major benefit is the environmental impact, or more accurately, the reduction of long-term orbital pollution. Without intervention, the growing cloud of space debris threatens to create a scenario called the Kessler syndrome, where cascading collisions could make entire orbital regions unusable for generations. AI-powered systems help mitigate this risk by enabling active debris removal missions, which target and deorbit larger pieces of junk before they trigger further fragmentation. By cleaning up existing debris and preventing new collisions, these systems play a key role in preserving Earth's orbital environment for future generations. The environmental advantages go beyond just reducing debris. They also contribute to the sustainability of space exploration and satellite operations. By maintaining safer orbits and extending the lifespan of functional satellites through collision avoidance, AI systems reduce the need for frequent replacements. Fewer replacement satellites mean fewer rocket launches, which in turn reduces the carbon footprint associated with space activities. In a way, these systems are helping to create a cleaner, more sustainable future both in orbit and on the ground. Now, imagine a future where Earth's orbital environment is managed with the same care and precision as a protected natural ecosystem. Instead of a chaotic junkyard of defunct satellites and drifting fragments, we could have a well-organized, debris-free space that supports innovation, exploration, and communication without fear of collisions or environmental degradation. Just as we've learned the importance of conservation and pollution control here on Earth, these AI-powered systems represent our commitment to responsible stewardship of space, a resource that is becoming as vital to humanity's future as the oceans and forests are to life on our planet. Ultimately, AI-powered systems offer a glimpse of what's possible when advanced technology meets forward-thinking responsibility. They're not just solving the space junk crisis, they're setting the stage for a new era of sustainable exploration, ensuring that the benefits of space remain accessible for everyone. So how far can we take these technologies, and what challenges remain in scaling them up? Let's move forward and explore what's next on this incredible journey. While the benefits of AI-powered systems in managing space junk are undeniable, it's critical to address the challenges and ethical considerations that come with deploying such advanced technology. Like any groundbreaking innovation, this approach isn't without its complexities, and understanding these potential downsides is essential if we are to create not just effective solutions, but responsible and equitable ones. One major challenge lies in the high cost of developing and deploying these systems. Designing, testing, and launching autonomous spacecraft equipped with AI, robotics, and the necessary sensors is no small feat. These missions require significant financial and technological resources, often making them inaccessible to smaller organizations or countries with limited budgets. While some nations and private companies are spearheading these projects, the question arises: how can we ensure that these advancements benefit the global community rather than deepening disparities between nations? After all, space is a shared resource used by countries and organizations worldwide. If only a handful of wealthy entities have the ability to clean up orbit, does this create a dynamic where they also control how space is managed? Then there's the issue of technical limitations. While AI is remarkably effective at tracking larger objects and predicting their trajectories, handling smaller debris remains a significant hurdle. Tiny fragments, some less than a centimeter wide, may seem inconsequential, but they can cause immense damage due to their high velocity. These fragments are difficult to detect with existing radar and tracking systems, and even when identified, capturing or neutralizing them presents a major technical challenge. Removing a large, intact satellite is one thing. Corralling millions of scattered fragments is an entirely different level of complexity. This limitation forces us to ask, will our current efforts be enough to address the full scope of the problem, or are we just scratching the surface? The risks of AI errors or malfunctions in space also cannot be ignored. While artificial intelligence is extremely advanced, it is not infallible. A malfunctioning system could miscalculate a debris trajectory, fail to capture a targeted object, or even collide with operational satellites, potentially creating more debris rather than reducing it. In a remote and hostile environment like space, where real-time human intervention is limited, even minor errors can escalate into major incidents. For example, what happens if an autonomous spacecraft pursuing a piece of debris accidentally damages a satellite providing critical services, such as weather forecasting or global communications? These scenarios raise questions about liability and accountability. Who is responsible when a system malfunctions? The nation or organization that deployed it, the manufacturer, or some other party? Ethical considerations add another layer of complexity. Space, by nature, is a global commons, but its governance is still driven largely by national interests and commercial priorities. Who gets to decide which debris is removed and when? There's also the issue of ownership. According to international space law, objects launched into space remain the property of the nation or entity that sent them, even if they are no longer functional. This means that removing a defunct satellite or rocket stage could technically infringe on a nation's rights. For instance, what if a company wants to remove a piece of debris belonging to another country, but that country says no? Or what if debris removal activities are perceived as a cover for other agendas, such as espionage or military dominance in space? These scenarios highlight the need for clear guidelines and mutual agreement on how debris removal should be carried out. This brings us to the critical role of international cooperation and regulation. Space junk is not a problem any single nation or organization can solve alone. It transcends borders and politics, requiring a unified global effort. Establishing international standards for debris tracking, removal, and even prevention is essential to ensure that all parties act responsibly and fairly. Collaborative initiatives such as treaties or agreements under the United Nations could help address concerns about sovereignty and ownership while promoting transparency and trust. Likewise, involving private companies in these discussions can ensure that commercial interests align with the broader goal of sustainability in space. Ultimately, the challenges and ethical dilemmas surrounding AI-powered space junk management underscore the importance of a balanced approach. While the technology offers incredible potential, it must be deployed thoughtfully, with careful consideration of its limitations, risks, and implications for global equity. In the end, creating a cleaner and safer orbital environment isn't just about what's technologically possible, it's about how we, as a global community, choose to collaborate and share responsibility for the future of humanity's presence in space. So, as we look to the stars and move forward with these innovations, let's ask ourselves, how can we ensure that progress in space benefits everyone, not just a privileged few? Real-world advancements in space junk management haven't just been hypothetical, they're already happening. Several pioneering projects and success stories have demonstrated the power of AI-driven systems to tackle one of the most pressing challenges in space exploration. These efforts, led by governments, private companies, and research institutions, are not only making strides in cleaning up Earth's orbit, but also illuminating the path toward a safer, more sustainable future in space. Let's take a closer look at a few groundbreaking initiatives that are leading the charge. One of the most exciting and well-known examples is Astroscale's ELISA program, short for End-of-Life Services by Astroscale. Based in Japan and the United Kingdom, Astroscale is a private company dedicated to advancing technologies for orbital debris removal. the ELISA program focuses on cleaning up defunct satellites and other large debris in low Earth orbit. In a key milestone, ELISA successfully demonstrated its debris-capturing technology in a test mission launched in 2021. During the mission, a spacecraft was equipped with a magnetic plate that locked onto a simulated piece of satellite debris, proving that the technology could autonomously locate and capture objects in space. This success not only showed the feasibility of active debris removal, but also highlighted how AI-driven systems could handle the complex task of precision navigation and docking in Earth's orbit. The mission reinforced the idea that autonomous cleanup efforts are both achievable and scalable. Astroscale's ELISA program has also brought important lessons to the forefront, most notably the necessity of designing future satellites with cleanup in mind. Their test mission relied on a magnetic plate to capture debris, which works best with satellites pre-equipped with the necessary docking hardware. This insight has inspired conversations about creating universal design standards for future satellites, ensuring that they can easily be deorbited or retrieved at the end of their operational lives. Such standards would prevent the creation of new debris while paving the way for the next generation of responsible space operations. Another standout initiative is NASA's use of artificial intelligence for debris tracking and avoidance. NASA has long been a leader in monitoring space debris, contributing data to the United States Space Surveillance Network, which tracks thousands of objects in orbit. In recent years, NASA has begun integrating AI into this process to enhance tracking accuracy and efficiency. Using machine learning algorithms, these systems can analyze data from radar, telescopes, and other sensors to predict debris trajectories with remarkable precision. For example, in 2018, NASA partnered with private companies to develop AI-based collision avoidance systems. These experiments have shown that AI can significantly reduce the chances of false alarm situations where debris is mistakenly identified as a threat, causing costly satellite maneuvers. By refining these systems, NASA is helping to make space operations safer and more efficient for the entire global community. It's also worth mentioning the European Space Agency's advancements in AI-based collision prediction. Through projects like the Space Safety Program, the agency has developed AI algorithms to predict high-risk collision scenarios and recommend preventative actions for satellite operators. In one notable instance, their AI-powered system successfully detected a potential collision between a European research satellite and a debris fragment. With the system's input, the satellite's operators executed a precise maneuver to avoid the object, demonstrating the practical value of AI in real-world scenarios. This program has become a model for how regional space agencies can collaborate with private industry to introduce cutting-edge technologies into everyday operations. One of the most promising aspects of these projects is the collaborative spirit behind them. Governments, private companies, and research institutions are working hand in hand to address the shared challenge of space debris. For example, Astroscale is partnering with national space agencies, including the Japan Aerospace Exploration Agency, to test its debris removal systems on larger international platforms. Similarly, NASA and private sector companies like SpaceX are actively exploring ways to integrate AI into satellite constellations, ensuring their long-term sustainability. These cross-sector collaborations underscore the understanding that space is a global commons, and solving its challenges requires collective effort. The success of these pioneering projects is as much about innovation as it is about inspiration. Each breakthrough moves us closer to a future where space remains accessible and safe for all. These initiatives not only highlight the potential of AI in addressing orbital debris, but also showcase humanity's ability to rise to even the most daunting challenges with ingenuity and cooperation. Through continued investment, experimentation, and collaboration, it's clear that we are well on our way to turning the dream of a cleaner, safer orbital environment into a reality. So, with these inspiring case studies in mind, it's impossible not to feel hopeful about the future of space exploration and sustainability. As we look to the future, the role of artificial intelligence in sustaining space exploration is set to grow exponentially. The next few decades will bring advancements that push the boundaries of what AI can achieve in managing orbital debris, safeguarding vital space activities, and enabling humanity to expand its reach into the cosmos. From swarms of autonomous cleanup satellites to global AI-driven initiatives, these innovations promise to address space debris on an unprecedented scale, while laying the foundation for ambitious projects like space mining, lunar exploration, and even Mars colonization. One of the most exciting trends on the horizon is the concept of AI-powered satellite swarms designed for orbital cleanup. Imagine dozens or even hundreds of small, agile satellites working together in perfect coordination, each equipped with AI systems capable of detecting, tracking, and capturing debris in real time. Rather than relying on a single spacecraft to tackle one object at a time, these swarms could divide and conquer, streamlining debris removal on a massive scale. Recent advances in AI algorithms, particularly in areas like swarm intelligence and cooperative learning, are making this vision increasingly feasible. These systems would operate much like bees in a hive, communicating and collaborating to optimize their movements and achieve their shared goal. For example, a swarm could assign tasks dynamically. While one satellite focuses on intercepting a larger object, others could handle smaller debris in the vicinity, ensuring efficient coverage of high-risk areas. Machine learning is another area poised to revolutionize space junk management. Current AI systems are already impressive, but next-generation models are expected to learn and adapt even faster. These advancements will allow for significantly improved predictive modeling, enabling scientists and operators to forecast debris trajectories with near-perfect accuracy. This level of precision will be crucial not only for avoiding collisions but also for planning future satellite launches and missions. By analyzing vast datasets, such as object behavior, orbital decay patterns, and even environmental factors like solar activity, these models could identify debris hotspots and predict where new risks might emerge. Think of it as developing a weather forecast for space, a tool that could help satellite operators plan safer maneuvers and governments implement more effective regulations. International collaboration will also play a central role in the next phase of AI-driven space junk management. The challenges of orbital debris extend beyond national borders, making a unified approach essential. In the coming years, we may see the emergence of global AI-powered initiatives led by coalitions of governments, space agencies, and private companies. These programs could standardize debris tracking, sharing data across platforms and countries to create a cohesive picture of Earth's orbital environment. For instance, an international AI framework could assign cleanup missions to the most capable systems, regardless of which organization developed them, ensuring that resources are allocated efficiently. Such collaboration wouldn't just improve debris management, it would also foster greater transparency and trust among nations, reducing the risk of conflicts over shared orbital spaces. Perhaps most intriguingly, these advancements in AI could unlock entirely new possibilities for space exploration by ensuring the long-term safety and sustainability of Earth's orbit. Consider the potential impact on space mining, a field that aims to extract valuable resources like water, metals, and rare minerals from asteroids or the Moon. Without reliable debris management systems, the risks of launching and operating mining missions would be far too high. Similarly, plans for lunar bases or Mars colonization hinge on having clean and accessible orbital pathways for transporting supplies, equipment, and people. By preventing the Kessler syndrome and maintaining safe orbits, AI could serve as the backbone of humanity's boldest endeavors. The question we must ask ourselves is this: what role do we see artificial intelligence playing in making space exploration sustainable and accessible for everyone? As these technologies evolve, they challenge us to think not only about technical solutions, but also about the kind of future we want to build. Will we use AI to ensure that space remains a shared and protected resource, or will we allow it to become yet another domain of competition and inequality? These are questions that demand thoughtful, collective answers as we move forward into this exciting new era of exploration. As we close this journey into the urgent challenge of space debris and the incredible promise of artificial intelligence, let's take a moment to reflect on what we've explored. Earth's orbit, once a symbol of infinite possibility, is now facing a growing crisis, with millions of pieces of debris hurtling through space at unimaginable speeds. The risks to satellites, space missions, and even the future of exploration are too significant to ignore. But amidst this daunting challenge, AI-powered systems are emerging as a beacon of hope. These transformative technologies provide precision, speed, and scalability that human effort alone cannot achieve. From tracking and predicting the movement of space junk with astonishing accuracy to deploying autonomous spacecraft capable of capturing and deorbiting debris, AI is reshaping how we approach the problem. It's not just about cleaning up the orbital environment, it's about safeguarding the technologies that power our daily lives, from GPS and telecommunications to weather forecasting and global connectivity. And beyond that, it's about preserving the possibilities of space exploration for generations to come. We've seen how innovative projects like Astroscale's ELISA mission and NASA AI-driven collision avoidance systems are already making a difference. These initiatives are more than technological feats, they're stepping stones toward a sustainable, cooperative future in space. But more importantly, they highlight the critical balance between innovation and responsibility. As we push the boundaries of what's possible with artificial intelligence, we're reminded of the unique opportunity and obligation. We have to ensure that progress benefits everyone. The path ahead won't be without challenges. Issues of funding, international collaboration, ethical considerations, and technical limitations still stand in the way. But what's clear is that the tools to address these challenges are within our reach. The very same AI systems we've discussed today represent not only solutions to space debris, but a broader shift in how humanity can harness technology to solve its most complex problems. So, as we look to the future, the question isn't just how we tackle space debris, but what kind of future we want to build both in orbit and here on Earth. Will it be one defined by innovation with purpose, by cooperation over competition, by a shared commitment to preserving the resources that sustain us? That choice is ours to make, and it begins with conversations like these. If this topic sparked your curiosity, we'd love to hear your thoughts. How do you see AI shaping the future of space? What challenges or opportunities do you think we're yet to unlock? Let us know in the comments below. And if you're as fascinated by the possibilities of futuristic technology as we are, don't forget to like, share, and subscribe. Together, we can keep exploring the incredible potential of innovation to create a better tomorrow, both above the Earth and here at home. Thanks for watching, and we'll see you in the next video.